Hello dear students, welcome back to NEET WORLD. So today we will be discussing thermodynamics 4 marks question for your IPE exam. Okay, so this session will be useful for both Telangana and AP students, those who are preparing for IPE exams. Okay, so for both BIPC and MPC students can use this discussion. Okay, right here. This is our C60 material. So this C60 material contains all the important questions for first year chemistry subject, as well as we have for mathematics, physics if you are an MPC students, and if you are an BIPC students we have chemistry, physics as well as biology. Okay, now you can access this C60 material like 60 out of 60 materials, like full out of full marks materials that are specifically designed for Telangana and AP students from our NEET WORLD, that is what Med World app here. So we have a Med World app. In this app you can download these PDFs for free of cost and you can use them for your preparation. Okay, so what to do? So just go to Med World app in the Play Store and download it, then just mention hi in the chat box, then our team will respond and they will be sharing you this C60 material. Okay, and there will not be any cost for this, it's a free of cost, you can completely access them and you can utilize them for your preparation. Because why we are providing this, we know in the market there is no such material which gives you perfect crystal clear explanation of each and every question that are very important for your IPE exam right now. So by looking at that, we have created this material and we have designed them for all MPC and BIPC students, and you can now use them and you can make your preparation more effective, and you can share these things with your friends, those who are also preparing for IPE exams, whether they can be first year or second year. For both we have the materials. Okay, right. Now today's discussion is on thermodynamics. Okay, today's discussion is on thermodynamics. So in the last sessions we have completed LAQ, discussion of LAQs. Okay, complete LAQs. We can expect LAQ questions from where? It is from structure of atom. Okay, structure of atom, and the next classification of elements, then next organic chemistry right now, and there are few chances to ask from chemical bonding also. Okay, right, all these LAQ questions are already discussed. If you haven't watched, you can watch them. And the next, what about this chemical bonding is, in the last class we have discussed chemical bonding, half of the chapter right now. Okay, so it means I just wanted to add a few more questions to this chemical bonding. Yes, we will do that, and before that I just wanted to start our discussion of SAQ questions from thermodynamics. So in this session we will be discussing thermodynamics first. Okay, right, look at here. So here, yeah, so in this thermodynamics there are few important questions to be focused for SAQs. Guys, whatever the questions we are giving here, so these questions are designed by looking at the previous year papers of IPE from both Telangana and AP states. Okay, so these are most repeatedly asked questions. Okay, that's why we have made a list of important questions, and the next, for each of that important question proper explanation is given in this manner. So this is the material. So if you open that PDF from the app, you will get answer like this for each question. Okay, right, and explanation of that questions will be provided in this NEET WORLD NEET WORLD YouTube channel here itself. So everything is free of cost. You can use them for productive preparation and you can have a very effective preparation for your exam. Okay, right, look at here. State and explain Hess law of constant heat of summation. Okay, what they are saying, state and explain law of constant heat summation. So very easy. See, what do we mean by Hess law here? I will tell you a simple way to understand this. First look at here. See, I am just preparing CO2. So preparation of CO2 are like production of CO2 from carbon can be done directly using C plus O2 gives rise to CO2. So production of CO2 taking place in single step. This is only in one step right now. Now we can also produce a CO2 with a different steps also, with multiple steps also. For example, here I am adding C plus half O2 gives rise to CO, carbon monoxide. This is step 1, I am saying this is step 1, and again the CO formed in step 1 is combining with 1/2 mole of oxygen and forming here CO2, and this is step 2. So now what is the difference from this initial reaction and this two-step reaction. So both are giving you the final product CO2 only now. Yes. So no matter whether a reaction is taking place in single step or in multiple step, the amount of heat released will be equal in both cases. For example, here X amount of heat or delta H amount of heat is released, delta H1 amount of heat is released in the first reaction I am saying, in this first indication I am saying. Now from this reaction, let us say this is the amount of heat released is, let us say here I am saying delta H2 and this is delta H3. Okay, this is the amount of heat released. Now what I am saying here, just the delta H1, that is heat released in the first reaction, is nothing but sum of heat released in these two steps, because these two steps are also giving the same product now. So the amount of heat released in this single step will be same as the amount of heat released in this multiple steps. Okay, the sum of this multiple step, that is delta H1 is nothing but delta H2 plus delta H3. So this is what law of heat summation. Okay, so is this correct? So just look at here, Hess law states that total heat change in a chemical reaction is the same. The total heat change will be same whether the reaction takes place in a single step, yes, whether the reaction takes place in a single step or the reaction takes place in a multiple steps. So whatever the heat change you are seeing in the single step reaction will be same as the heat change that is taking place in these multiple steps. Okay, so overall will be same value only, whatever the heat change in the single step will be same as in this multiple step for production of CO2 from carbon and oxygen. Okay, this is what the Hess law says here. Okay, is this clear? I hope this is clear. Okay, for example, I am saying for this the heat change is X. Okay, what I am saying, the heat change is X. Now for this I am saying it is Y, and for this I am saying it is Z. Now X will be equals to Y plus Z, that's it. This is what they are saying. So why I am saying this X, Y, Z value, just to make you clear. For X value they may give something like minus 200 I am saying. For example, I am saying here minus 200. So here let us say it is something like minus 80. Here it is minus 120. Therefore minus 200 only na both values. Yeah, like that you can understand. Okay. So that's it. This is about law of a constant heat summations. Okay, so now explanation, just see here explanation. So that is what the exact example I have given. So in the exam point of view, yes, you can represent that example. Along with this, you just extend your answer. See, we need to give a proper presentation in the exam now. So that's why you just mention in this way. Then after you can give a real example. See what I am saying, explanation. Consider a chemical reactions where a substance A changes to D. So A is a reactant converting into final product D here. Okay. So now formation of D from A can directly takes place in single step. See A to D, a direct path, that is path 1. It's a direct step. So here delta H I am writing. Okay, heat changes delta H. Now indirect method, it means first A is forming instead of like this, A is going to form B, and now B is going to form C. Now C is finally converting into our D. Okay, so now in this process whatever you are seeing, A is giving rise to finally D only now. So if you remove like this, you have only A to D. So for example I am saying this, for this process delta H1, for this process delta H2, for this process delta H3 I am saying. Then next, what about enthalpy change for this final step, that is delta H, is nothing but adding all these values will give you the final answer. So delta H1 plus delta H2 plus delta H3, that's it. This is what you need to do here. Okay, so here you can see A to B I am saying Q1, B to C as Q2, C to D as Q3, then delta H1 is equals to Q1 plus Q2 plus Q3, that's it. This is what you need to mention. Sir, is it's useful for NEET? Yeah, actually those who are in the chat box asking whether it is useful for NEET, yeah, to be frank dear, these sessions are for IPE. Okay, IPE means it's a board exam conducted in Telangana and AP states for intermediate class 11th and class 12th students. Okay, so it will be more useful for them. And since you are asking me about NEET, yes, I suggest you, yes, this concept is there in NEET also, but I suggest you to join our free EAP set sessions. I mean, we are doing NEET EAP set and JEE live sessions every day. See, I will be having today at 5:30 I will be coming up on electrochemistry for EAP set, JEE and NEET exam point of view. Okay, so you just join those sessions, then that will be definitely useful for you. Okay, those who are asking in the chat box, I am saying for them. Amina, I think Amina sir, it's useful for NEET. No, yeah. So this is about the thing. I hope I given you clarity about your question, right? Now let me give you few more explanations here. Here according to Hess law, so what you can say according to Hess law here, if total heat change in the direct path is pi 1, then for indirect path it is given as pi 1 is equals to pi q1 plus q2 plus q3. That is what we have discussed till now. So these are the experimental data, I mean perfect values I have given. For example, C plus O2 gives rise to CO2, that is what we have discussed. Enthalpy changes exact value is something like minus 393.52. Okay, then indirect reactions will be like this. So how do you do this? Just add delta H1 plus delta H2 from these multiple steps that which are giving you final product as CO2 as in the first step. So that is nothing but delta H is equals to delta H1 plus delta H2, that's it. Okay, that's it. So this is about Hess law question, that is 4 marks, very important questions for your 4 mark. Okay, then next here, state first law of thermodynamics, explain its mathematical form. So it is very easy. The first law of thermodynamics states like it is nothing but the energy can neither be created nor be destroyed, but it can transform from one form to another form. Just remember this. So energy can neither be created nor be destroyed, it can be transformed from one form to another form. It means you are converting electrical energy to mechanical energy or mechanical energy to electrical energy like this. So from one form to another form you can convert, but destroying it or creating it will not be possible, that is what they are saying. But we can transform or we can convert from one form to another form, that's it. Okay, right. So a new energy cannot be created, but it can be transformed from one form to another form. Okay, right. So now what you can remember, energy of the universe remains constant. What I am saying, energy of the universe remains constant because in the universe energy can transform from one form to another form. Okay, it means convert from one form to another form, but it cannot be created newly. Okay, so it means energy of universe will remains constant. Remember this. This is first law of thermodynamics. Okay, and after that you just see mathematical equation here. See what is the mathematical equation here, you can see delta E is equals to, you can write delta U or delta E. E means internal energy, or you can also indicate with a delta U, that is also internal energy, will be equals to Q plus W I am saying. So Q plus W here, depending upon the W work done, we will be changing the sign. Okay. So now here delta E is means what, delta E is nothing but E2 minus E1, E2 minus E1. So what is E2 here? So this is final, E1 is final initial internal energy, and this will be final internal energy. Therefore delta E means change in internal energy. Okay, right. And what about Q here? Q is heat, like heat here, see Q is heat absorbed from the surroundings like that. Increase in internal energy is given as the following way. Okay, W is work done here. Okay, so now look at here, the formula will be mentioned in this way. So it depends on what way you are indicating. See delta E U, like delta E is equals to Q plus W we can indicate. Okay, or here you can see the Q minus W equals to delta U. Both ways are correct, only here they are directly saying that heat is like work is done by the system. So here I am just mention work done, here they are saying work done by the system, that's why we have got negative sign there. Okay, so you can transform this one from here to here, like sending W this side, you will get Q equals to delta E plus W. So both ways are correct, only representation. Okay, you need to specifically mention that whether it is work done by the system or work done on the system, that's it. Next, here you can see one more thing, state the third law of thermodynamics. What do you understand by it? See, entropy, its third law says about entropy change. Okay, see the entropy of a pure and a crystalline substance, perfectly crystalline substance, pure and perfectly crystalline substance is 0 at absolute 0 temperature. It means at 0 Kelvin, I am not saying 0 degrees, it is 0 Kelvin, absolute 0 means 0 Kelvin. The entropy of a pure and perfectly crystalline substance will be 0. What they are saying, the entropy of pure and perfectly crystalline substance is 0 at absolute 0 temperature. That means when temperature of perfectly crystalline solid approaches 0 Kelvin, that is minus 270 degrees, its temperature will also approaches to 0. Okay, when entropy 0, its temperature, like when temperature approaches 0, its entropy also approaches 0. Okay, remember. So explanation, at 0 Kelvin all molecular motions are stops. It means there is no kinetic energy here, there is no movement of particles. Okay, so all molecular motions are stops. The particles are perfectly arranged in an orderly manner. Okay, there is no randomness. What do we mean by entropy? So this is nothing but, entropy is nothing but measure of disorderness, measure of randomness. Now, so at 0 Kelvin, at what temperature? At 0 Kelvin, what happens? There is no movement of particles, there is no motion of particles. It means particles are perfectly arranged. See, particles are arranged in an orderly pattern. If everything is orderly arranged, then there is no randomness. No? So randomness is 0 means the measure of disorderliness, that is entropy change, also 0. That is what they are saying. The at 0 Kelvin for a perfectly crystalline pure substance, the entropy change will be 0. Okay, remember this. So hence the system has only one microstate, therefore no disorderness. As a result, the entropy becomes a 0. Okay, that's it. So now this is how you can indicate. This is how I will tell you how to indicate here. So just take delta S, temperature, this is at 0 Kelvin. Okay, like this will be equals to 0. Okay, what I am saying, for entropy, see here, limit tends to 0, that is entropy change will be equals to 0 according to the third law of thermodynamics. S is equals to 0 at absolute 0 for a perfectly crystalline substance. Okay, right, this is about third law of thermodynamics. Now we have heat capacity. This is one more question, that is heat capacity. So what do we mean by heat capacity here? Let me explain. Define heat capacity and what is the relation between CP/Cv. So CP/Cv relation they are asking. This is also important questions. See, whatever you are learning for IPE exam, definitely useful for your competitive exams like NEET, JEE and EAP set also. Okay, so just try to understand the concept and solve some previous year questions or the numerical type questions for your competitive exams, JEE, NEET and EAP set, after the understanding of this concept first of all for your IPE exam. Okay, because IPE exams are very close. First focus on IPE now, and then next you focus on your EAP set, because you are first year students only now. Since you are first year students, you have lot of time, I mean one more year of time for your JEE, NEET and EAP set exams. So what I suggest, first focus on your IPE marks. Like this time you should get maximum marks possible, because you know in the next year you will be very busy in your preparation for your NEET, JEE and EAP set preparations right now. Therefore you will get very less time and you will be concentrating more on competitive exams than this IPE exam right now. So that's why this is the time you, in the first year itself you should score maximum marks in your IPE. Even if there is any less marks in your second year, you won't feel bad about that, because you already scored very good marks in first year, so it will be cover up. Okay, anyways you are going to get good marks in second year also, because you will be having parallel preparation. Whenever you are preparing for competitive exams like NEET, JEE and EAP set, you should focus on concept. So when you focus on concept, automatically you can express or you can present your IPE answer also very effectively without concept. Okay, you no need of by hearting the things. Okay, so when you learn the concept, yes, you can write any type of exam, whether it is theoretical, descriptive like IPE exams, or whether it is a competitive objective type exam also. Okay, so first of all focus on concept learning. Okay, right, look at here, define heat capacity and what are CP/Cv, show the relation between them. Okay, so now heat capacity is nothing but, so the heat capacity of substance is the amount of heat required to rise the temperature of substance by 1 degree or 1 Kelvin. Okay, so for example, there is a substance here. Now the amount of heat supplied to this substance to rise its temperature, for example its temperature is now T. Okay, now what is the amount of heat required to rise the temperature of this substance from T degrees Celsius to T plus 1 degree Celsius. Okay, so the amount of heat required to rise the temperature of the substance by 1 degree or 1 Kelvin Celsius, 1 Kelvin temperature is called its heat capacity. Okay, now heat capacity will be given as Q by delta T. What I am saying? Q by delta T, I mean dt. Change in heat, see Q is directly proportional to change in heat. I mean whatever the change in heat depends on what amount of heat supplied. So that is what directly proportional here we are writing. Okay. So now what you can say here? What you can say, so delta T is equals to, they have written it as like delta T here, just remove proportionality and replace with a constant C. So C indicates what? Heat capacity. So that is nothing but C is equals to Q by delta T, that's it. Okay. So this is what you are going to write. First you write this relation, Q is directly proportional to delta T, and from that you can write this equation, and after writing that, so what do we mean by C? C is called heat capacity and Q is called heat absorbed, and delta T is rise in temperature. Okay. So what is the amount of heat rise, temperature raised by supplying Q amount of heat? Okay. If I supply Q amount of heat, if the temperature changes 5 degrees, then our delta T value is 5 now, like that. Okay. So now there are different types of heat capacities. I can say heat capacity measured at constant pressure, that is Cp. What I am saying, heat capacity is measured at constant pressure is called Cp. It means, for example, I am measuring it for a 1 mole of substance, then I can say molar heat capacity measured at constant pressure, that is indicated with Cp. Okay. Here if I say the amount of substance in grams per gram of substance, if I say, you should call it as specific heat capacity. What I am saying, per gram of substance you should say it as a specific heat capacity. Per mole of substance you should say molar heat capacity. It means, how do you define this? The amount of heat required to rise the temperature of 1 mole of a substance by 1 degree Celsius is called its molar heat capacity. Okay. So if it is per 1 gram, you can say specific heat capacity. Okay. Then next, now at constant pressure you should indicate with Cp, symbol Cp. So now what it is, the heat capacity measured at constant pressure is called like Cp value here, molar heat capacity at constant pressure. Similarly, if I say Cv, it is a heat capacity measured at a constant volume, then we can say Cv. Now what is the relation between this Cp and Cv? So we know there is a relation between enthalpy and internal energy. What is that enthalpy? H is equals to U plus PV we are writing right now. So for an ideal gas, PV is equals to RT for 1 mole of a gas right now. For 1 mole of an ideal gas, PV equals to RT we can write. So from this you can write here H is equals to U plus, wherever I have PV, I can write this RT. So I am writing RT here. Okay. Now change in enthalpy, that is dH is equals to du plus R dt, because R is a universal gas constant, that's why I am writing here UV formula I am applying, d by dx of like differentiation of UV formula I am applying. Since R is a constant, we will get R dt only. Okay. So now from this what I am doing is dividing all the sides with dt. So dH by dt, you need to write this derivation to get good marks. Okay. dH by dt by du by dt is equals to R, because dt cancel this side, this will be plus R here. Okay. That's it. So now here we got enthalpy change by temperature change. So this term is called Cp, molar heat capacity at constant pressure, and this is called Cv, molar heat capacity at constant volume plus R. Okay. From this you can write Cp minus Cv is equals to R. So this is a relation between Cp Cv for 1 mole of a substance. Okay. Is this clear? So I hope this derivation is clear. So I will be providing you the same derivation in the book also. See here, H means enthalpy, U means internal energy. Now differentiate this, differentiate with respect to temperature. Therefore it becomes dH by dt equals to du by dt plus dPV by dt. That is what we have mentioned in the previous discussion also. Finally you got Cp minus Cv equals to R. So this is about our discussion on heat capacity terms. Okay. This is also important question mark. Okay. So first one is that one Hess law question, and the next Cp Cv relation question also important things you need to focus for your IPE exams. Okay. Then next we have few questions to be discussed from like equilibrium chapter. So let us start our discussion of this equilibrium questions also, because yeah, we need to cover as many questions as we can. Okay, so now look at here, derive the relation between Kp, Kc for an equilibrium reaction. Okay, so how do you write this? They are asking what is mean by Kp, Kc and its relation. Very easy. See, Kp means Kp, Kc. First of all, you need to understand Kc means you are expressing equilibrium constant in terms of concentration. In terms of what? Concentration. And when you say Kp, you are expressing equilibrium constant in terms of partial pressures. Okay. Okay, so now Kp means molar concentrations, Kc means molar concentration, Kp means partial pressures of that gaseous substances. It means I will tell you what exactly equilibrium constant means. First of all, let us take one equation like production of ammonia through Haber's process. This is what the equation now. Now you can see all of this can be in gaseous state. Ammonia can be gas, hydrogen, nitrogen, everything can be gaseous phase here. So now if I want to express equilibrium constant for this reaction, what I can do? I can write this equilibrium constant in terms of molar concentration. It means molar concentration of ammonia, concentration of NH3 to the power 2, whatever the stoichiometric coefficient is there, you write it. Okay, by concentration of N2, whatever the stoichiometric coefficient here 1, no? So write it here, it has 1, and concentration of H2 to the power its stoichiometric coefficient 3, like this you can write. Okay, this is about Kc. Okay, and after this Kc you can also mention it for Kp. So what is Kp here? You are expressing same thing, I mean activities only, but in terms of partial pressures. It means partial pressure of like ammonia here product. Okay, whatever the coefficient you have, you write here, and the next here partial pressure of N2 to the power 1 and partial pressure of H2 to the power 3. Now what is the relation between this Kp, Kc they are asking. Okay, it is very easy. Now in order to get that, you need to know about ideal gas equation, that is PV equals to nRT we are writing now. So from here I can write P is equals to N by V RT. So what do we mean by N by V? This is molarity only now. So I am indicating that molarity concentration with a square bracket. So here P is equals to square bracket here R into T it becomes. Okay, so P is equals to square bracket, that is concentration, R into T it becomes. Okay, so right here. So now what you can do here, wherever we have this partial like this pressure, there you can write this square bracket, it means this one into RT. Okay, so it means just observe here what I have mentioned in this place, wherever I have Kp, so in the place of P, wherever I have pressure, I can write this square bracket indication of concentration of NH3 power 2 and RT power 2. Why? Because partial pressure of PNH3 means from this equation what I can write? Partial pressure of ammonia will be equals to what happens here? Concentration of NH3 you can write multiplied with RT. Okay, RT, like this you can write. Since it has a square, you just square it here. So here also it will become squared. Okay, that means it becomes concentration of NH3 power 2 dot RT power 2, like this it becomes right now. So in the denominator also, here you will get P N2 into RT power 1. Okay, and here you will get P H2, what is the power here we have cube now, so 3, and RT power 3 you will get, like this you will get. So this is a thing we can write in the place of K, like P. Okay, so Kp becomes like this. Now wherever you have concentrations, from that what you can write? So concentration of NH3 by concentration of, see here you have concentration of N2 and here you have concentration of H2 power 3. So in the place of these three things I can write Kc. So Kc into RT power 2, RT power 3 here, RT power 1 here. So it means RT power 4 in the denominator, RT power 2 in the numerator. So it becomes in the denominator as RT power, so I can cancel out these and here we will get 1 RT. Okay, so totally it is RT power 2 in the denominator. So you got finally Kp is equals to Kc into RT power minus 2, we can write it in the numerator like this. Okay, so now I will be giving you one simple relation for finding this. Kp is equals to Kc RT power delta Ng. So what do we mean by delta Ng here? So delta Ng is nothing but for all these gaseous species, I am saying only for gaseous species. So whatever the coefficients they have, like number of gaseous products minus number of gaseous reactants. Now number of gaseous products are how many? 2 here. So 2 here, it means delta Ng is equals to number of gaseous products are 2 and gaseous reactants are 3 plus 1 minus 4. Okay, that will be minus 2. That's why we got here minus 2. So this is a generalized equation you can use for Kp Kc relation. Yes, same relation will be useful for your EAP set, NEET and JEE preparations also. So what is the relation? Kp is equals to Kc RT power delta Ng. Okay, like this you need to indicate. Okay, is this clear or not? Guys, if this is clear, please click on the like button and tell me in the chat box if there is any confusion. If there is any confusion, please mention in the chat box. Abba. Okay, so if it is clear, let us move forward. So the next question here we have is Le-Chatelier principle. Okay, one of the very important topic for your competitive exam point of view also, along with your JEE, your IPE preparations. So look at here, what they are asking, state Le-Chatelier principle and apply it to the synthesis of ammonia by Haber's process. So what do we mean by Le-Chatelier principle? So if a system is at equilibrium, then if there is any disturbance occurs on that equilibrium state, then that equilibrium get disturbed and equilibrium moves to nullify that whatever the disturbance caused to it. So it means, just listen here, if a system is at equilibrium, is subjected to change in temperature. The disturbance is nothing but if there is any change in temperature or pressure or concentration, then equilibrium shifts in a direction to oppose or the counteract the applied change. For example, look at here, see A plus B is in equilibrium with C plus D. Now what I am saying here is, since it is an equilibrium state, it means at this equilibrium state, concentration of reactants, concentration of product will remains constant. What I am saying, their values, concentration of reactant and products will be remains constant. So whenever we increase the concentration of reactants, then this equilibrium will shift forward. Why it is shifting forward? Since you are disturbing at the reactant side, so to nullify this external disturbance, whatever you are applying stress is there now, to nullify this stress, equilibrium moves in a direction to nullify that stress. For example, I am increasing the concentration of reactant. Now what happens? Since concentration of reactants are increasing, then equilibrium gets disturbed. Why? Because at equilibrium concentration must be constant for reactants and product. But you are increasing the concentration of reactant, then equilibrium moves forward, so that whatever the increment value you are seeing here, that will be nullified by moving forward. Now one more way I can say, if I decrease the concentration of reactants, now what happens? then equilibrium moves backward, so that whatever the decrement in the concentration of reactant you are seeing, that will get balanced again. That is what the reaction favors backward when you decrease the concentration of reactant. Like this, we have this Le-Chatelier principle. What is the use of Le-Chatelier principle? It explains that at an equilibrium state, if any external stress is applied, then equilibrium will move in such a way to nullify that external stress. That's it. Okay, this is what you need to remember here. Okay, right. And then next, after this, if you see, what are the effects of temperature here we have, what is the effect of pressure we have, we need to look for Haber's process, ammonia preparation. Okay, see, application to the Haber's process, it means Le-Chatelier principle application to the Haber's process. You can see here what they are saying. See, here they have mentioned N2 plus 3H2 gives rise to 2NH3. So, the enthalpy change delta H for this process is minus 92 kilojoule per mole. So, this reaction is reversible and exothermic. So, this Haber's process reaction, this production of ammonia reaction is a reversible reaction and it is an exothermic reaction. It also results in decrease in volume. So, now what happens? See, the production of ammonia is a reversible process. Just remember, it's a reversible and exothermic process. Okay, so you need to remember this term exothermic. When we need to mention this term, whenever you are representing the enthalpy change as a negative value, like minus 92 kilojoule per mole, we are saying as per the experimental data. So it means this reaction, during the reaction, this much amount of heat is released. Okay, it's an exothermic. Okay, so now when this ammonia is produced, what is happening? Volume is getting decreased, because reactant side, if you see 1, 3, so 4 moles of like reactants are there, there is only 2 moles of product. It means 4 moles of reactant getting converted into 2 moles of product. It means you can say volume is getting decreased here. Okay, now look at here, effect of temperature. So what is the effect of temperature? Since the reaction is exothermic, so it means exothermic reactions means heat is releasing from the system now. So when heat is released, the system temperature decreases, system's temperature decreases. So it means reaction is moving forward by decreasing its temperature. It means the lowering the temperature favors the forward reaction, thus increasing the yield of ammonia. So if we make it low temperatures, then more amount of ammonia is produced. Okay, this is what you need to remember here. Next, what about the effect of pressure? See, effect of pressure, forward reaction causes decrease in volume now. So decrease in volume means high pressures are required. So since number of moles are less here, so it means volume will be less at the product side when product formed. So in order to maintain low volumes, we need to increase pressure. So the forward reaction causes a decrease in volume, therefore increase in the pressure shift the equilibrium towards ammonia formation. That high pressures, more ammonia is formed. What I am saying, high pressures, more ammonia is formed. Okay, remember this. Then next, now what is the ideal or optimum conditions for production of ammonia? So just look at here, temperature, optimum range is this much. So these are experimental values that we need to be remembered here. So temperature, the optimum temperature for production of ammonia is 725 to 775 Kelvin. Now pressure should be high pressure, that is 200 to 300 atm pressures, and concentrations here pure N2 and H2 is taken as a reactant so that ammonia is produced. Then next, what about catalyst? Catalyst used here is iron catalyst. What is that catalyst? Iron. And promoter used here is molybdenum. What is the promoter here? Molybdenum promoter is used. Okay, right. These are the things to be remembered from this discussion. Okay, the next here, can you do it for, can you make it for production of SO3, the synthesis of SO3 by Contact's process? See here, same Le-Chatelier principle is already we discussed. If there is any external stress is applied on the equilibrium, then equilibrium will shifts in a direction to nullify that external stress. This is what Le-Chatelier principle says. Okay, so now look at here, production or synthesis of ammonia by contact process. So now what they are saying here, formation of SO2 first. Okay, sulfur is burned in the air to produce sulfur dioxide. So you treat sulfur with oxygen so that it will give SO2. After formation of SO2, Now sulfur dioxide is oxidized in air to form sulfur trioxide. So SO2 is treated with O2, that gives SO3. Okay. So for this, what is the enthalpy change? Minus 189 kilojoules. Okay. The reaction is reversible and exothermic. What is this? This reaction is reversible as well as exothermic, and it is accompanied by decrease in volume. So how this reaction is produced? Like see, here you have 2 plus 1. Reactants are 3 and products, if you see, only 2 products are there. So number of moles is less now. So it means formation of product is favored by lowering of volume. So low volume means more amount of product is formed. Okay. So for that, the decrease in volume favors forward reaction, production of SO3. Okay. So from this you can also say that since decrease in volume favors forward reaction, so forward reaction involves a decrease in volume. It means high pressure favors formation of SO3. So the optimum pressure is how much? 1.5 to 2 atm pressures during the experiment. Okay. Then next, what about effect of temperature? See, effect of temperature, see, it is an exothermic now. Since the reaction is exothermic, low temperatures favors formation of SO3. Okay. So however, at too low temperature slows down the reaction rate. So what is the optimum or the specific temperature during the reaction? It is 673 to 723 Kelvin. Okay. So you just mention it is low temperature favors forward reaction as per Le-Chatelier principle, and optimum temperatures are 673 to 723 Kelvin. Okay. Remember this. Next, what about the catalyst used here? So it is finely divided V2O5, vanadium pentoxide or platinum is used to increase the rate of reaction. So you need to mention this catalyst also. In production of ammonia, you have seen iron as a catalyst. Okay, iron as a catalyst and molybdenum as a co-catalyst or a promoter there. So here vanadium pentoxide is a catalyst, or platinum also can be used here. Okay. So conditions are what? Temperature is 673 to 723 Kelvin. Okay. And pressure is here 1.5 atm to 2 atm pressure, and catalyst is V2O5 or PT, platinum. That's it. Okay. So this is about the discussion. Okay. Now we need to discuss a few more things related to ionic equilibrium here. So explain concept of Bronsted acids and Bronsted bases, illustrate with examples. Okay, right. So this question will be discussed in the upcoming session, in the next session, because here till now we have discussed thermodynamics as well as chemical equilibrium. So the ionic equilibrium part will be discussed in the upcoming sessions. So now what you do? So you just stay connected with this NEET WORLD channel. Okay, and learn the things that whatever we have discussed till now, and we will be meeting in the next session for your IPE discussion. Hope you have watched all the previous sessions of IPE. If not, just go and watch all these discussions of IPE and make your preparation more productive from our NEET WORLD YouTube channel. Okay, just go to live playlist and you can see chemistry IPE sessions, physics IPE sessions, and botany IPE sessions, zoology IPE sessions, as well as mathematics IPE sessions if you are an MPC students. Okay, right. So thanks for watching. Stay connected with us and you can share with your friends. Thank you. Sorry bro.